Hello, college algebra, and this is the video over 5.3, logarithmic functions and their graphs. Before we start the main lesson though, I need to refresh you on something. So consider this kind of like a bell ringer, but you're not really doing the bell ringer in class, so just roll with it. So rewrite the following root functions as a rational exponent. Or in other words, try and rewrite these as x to the power of a fraction, where the number on top is the power and the number on bottom is the root. You guys have done this before, so this is basically a refresher. So in other words, for this example, your root would be 7, so that would go on bottom. Your power is 3, so that would be on top. So this is the same it's basically the same expression, just rewritten as x to the 3 over 7. Now let's do the other one. This one, you can't really see what the power and the root is, but you know this has to be a power of 1, and the root has to be a power of 2. Using that knowledge, rewrite it as a fraction with the power of 1 on top and the root of 2 on bottom. And there you go. You will be seeing some examples where you'll have to do this, which is why I wanted to refresh you on that. So now that you've been refreshed on that, now let's go to the main course. Logarithmic functions, or you guys know them as log functions. The formal definition, if we let a be a positive real number not equal to 1, then the log function with base a is defined to be the inverse of the exponential function. So in other words, if you have an equation where your base is a number and then your exponent is x, you can assume that the inverse of that equation would have log with it, where this base number is ending up being here as the base number. And then your exponent would end up going here. So, well, scratch that last part. Mostly just remember that whatever base is here is the same as the base here. Or in other words, logs are inverses of these type of functions. And what we're going to talk about first is what do log functions look like in terms of their graphs? Well, as you guys remembered earlier this week, when we're dealing with these type of functions, basically their graphs, they always start at 0, 1. So if you look at this red graph over here, you'll notice that it starts at the point 0, 1. And this point over here also starts at 0, 1. That's how it is for any red AX function. Now for log functions, they also have a starting point very similar to it. Basically, it's the same point, only you switch the 1 and the 0 around. So instead of 0, 1, all log functions that you see in blue are going to start at 1, 0. And this one over here, as you can see, it starts at the point 1, 0. So just like before, when we learned about graphing these, we always started at 0, 1. For logs, they have a starting point as well. It's 1, 0. It's up to you to make that distinction between which is which. But for log functions, just remember 1, 0. That's where we always start. Now, another thing that's similar to what we learned earlier this week is looking at their bases. In this case, the number that's right next to the log, that is always the base. And just like before, if your base, well, that should actually be a B for base. Let me fix that real quick. B, here we go. If your base is between 0 and 1, then you're going to have a decreasing slope. And sure enough, look at that decreasing slope. And of course, it is going through the point 1, 0. Personally, when I look at this log graph, I always think it looks like a hook. So in other words, it looks like a decreasing hook. Like if you think about it, the way that it curves like that, it's kind of like, ooh, there's a hook. There's the little pointy end. That's what it looks like to me. But you can use it however you want. So if your base is between 0 and 1, your graph is going to be a decreasing hook. And just like before, if you have a base that is bigger than 1, or we'll change that to a b, if your base is greater than 1, you're going to have an increasing slope. And sure enough, just like over here, if you were to put a roller coaster on this little trail, it'd go upwards. Now this one I like to call an increasing candy cane. So INC for increasing, so increasing candy cane. Because the way it's curved, doesn't it look like it has like a little candy cane hook? Just kind of like, oh, there you go. Now I should probably put that in red though, because candy canes for the most part are red. So if your base is between 0 and 1, you're going to have a decreasing hook. If you have a base bigger than 1, your graph is going to have an increasing candy cane. And just like all log points, you're always going to start at 1, 0. So very similar to what you guys learned earlier this week, just a few slight changes. Then moving on to other stuff, very similar to what you guys learned previously, is that when you're doing horizontal shifts, flips, and vertical shifts, they have to go in a special order. You have to do horizontal shifts first, or HS. Flips go second, and then verticals go last. Just the same as before. So let me show you some examples. So let's say we have log base 3 of x plus 3 in parentheses, and then plus 2 on the outside. Well, first off, you know, without a doubt, we're always going to start at 1, 0. But then, let's take a look at our base. Our base is 3, which is greater than 0, which means we're going to have an increasing slope, or as you see here, an increasing candy cane. Okay, you didn't actually have to draw that. I just wanted to show you. Increasing candy cane. Increasing candy cane. So that's how you would start. You would start as this red graph going through 1, 0 in increasing slope. But now let's look at what we have in terms of shifts. The plus 2 on the outside is your vertical shift, meaning going up 2. The plus 3 on the inside is your horizontal shift. And remember, when you go left or right, you do the opposite of what you'd expect. So the plus would make you think to go right, but do the opposite, and you're going to go left 3. But remember, just like the previous slide said, horizontal shifts go first, vertical shifts go second. So let's do the horizontal shift first and go left 3. So take the point 1, 0, move it right 3 spots. 1, 2, 3. Okay, so temporarily we would be right there. And then we're going to go up 2 units. So starting here, you go up 1, 2. And thus, that is how we get the blue graph as our final answer. The blue graph here would be the final answer graph that you would pick on your online homework. Again, very similar to what you guys did earlier this week. Let's try another example. Again, remember, we always start at 1, 0, not 0, 1. That's for the other equations. Then look at your base. Your base is 1/2, which is between 0 and 1. So when it's between 0 and 1, you're going to have a decreasing slope or a decreasing hook. And that's how we start. And in this case, we only have one type of shift, a vertical shift going up 1 unit. So then start at 0, 1, go up 1 unit, bloop. And there you go. The blue graph is your final answer. Now, in terms of flips, the only type of flip that I've seen with these are when the negative is in front. And when the negative is in front, or specifically when it's outside the parentheses, it is going to reflect or flip over the x-axis. And I'll show you an example of this type on the next slide. So on this slide, you can't really see it on the video, but what it's saying is that the equation is 2 minus log to the 1/2 of x plus 4. And that's basically what it says. Now, I want to let you know, this is a positive 2 in the front being subtracted by log 1/2 of x plus 4. It looks a little weird when the log function's not in the front. So why don't we take this positive 2, move it to the back? So then this equation would be, I'm going to write over here, negative log, because remember we didn't move this negative, or that minus sign, so it stays in the front of the log. So negative log base 1/2 of x plus 4, and then that's positive 2 or plus 2 on the outside. So in other words, this is the function we're going to try and graph. So off to the side over here, well, first we're going to start off at 0, 1. Well, not 0, 1, 1, 0. We're going to start off with that and look at your base. Your base is between 0 and 1, which means we're going to have to decrease, or in other words, decreasing hook. And that's how we're going to start. And now let's just label everything we have before we do anything else. Here, that's our horizontal shift, and it's going to have to go left 4, because it's the opposite of what you expect. This is our vertical shift of up 2, and then this is our flip over the x-axis. Now remember, horizontal shifts go first. So in other words, I would take this graph, move it over 4 units, 1, 2, 3, 4. So in other words, I'd be right about here whenever I would do my horizontal shift of left 4. Because remember, horizontal shifts go first. And then second are the flips. So in other words, you're going to take that decreasing hook, and in this case, since it's already on the x-axis, you're basically just going to have to basically use the x-axis, or that point, as your rotating point. Basically, everything else will rotate, but that point will stay. So in other words, your hook will flip upwards to be like this, and your little stick will flip down like this. And then that would be your x-axis flip. And then last but not least, you can now do your vertical shift. Or in other words, take where you were at the x-axis and go up 1, 2. So in other words, your graph would look something like this, like a candy cane, only shifted upwards in the air. So that would be your vertical shift up 2. So knowing that, you know your graph, after doing all 3 of those, is going to have to look something like this. Now, with that in mind, let's compare that to these. Well, first off, it's definitely not going to be this one, because that's not even curved correctly. This one is curved in the candy cane style, but it's too low underneath the x-axis, so it can't be that one. So it has to be one of these two. They look very similar to the one that we're looking at. So let's think of it this way. We started here at 1, 0, but we do know that we moved over 4 units. And then we went up 2. So in other words, that one is not high enough. So it can't be that one. And then let's just double check this one. So we started here at 1, 0, and we moved over 4 units, and then we went up 2. So in other words, this one matches what we're looking for in terms of shifts and flips. And there you go. That's how you would tackle that one. So basically, just make sure you take into account each type of shift and flip that you do in order. And then once you have an idea of what your graph looks like, you can go to these and say, okay, this one fits the bill. And that, I feel like, the graphs are probably going to be the hardest part of this lesson. Once you understand that, the rest is easy. And now, away from the graph part, now let's talk about something that you guys clearly remember from Algebra 2. Way back when in Algebra 2, you learned about a trick called the loop method. And the loop method basically said you always started at this little base right here, and then you would loop to the outside, and then you would loop back to the part in parentheses. And the way the loop method worked is whatever came first, you would rewrite first. So the A came first, so you rewrite it first. The Y came second in the loop, so that means the Y would come second in the next equation. And you would rewrite that part as the power. And then that's going to be equal to the third part of the loop. Or in other words, the X. So in other words, the loop method would have you rewrite the equation like this, where the A came first, the Y came second, and the 3 came last, or the X came last. And that's where this statement comes from. The X is equal to AY, just like this, if and only if you have log AX of Y, which we do have over here. So that's just a refresher of the loop method if you need a refresher. Now let me show you how to use it in an example where you have to solve. So let's say you got these two log equations we got to solve for X. And we're going to solve them using the loop method. So start here at your base of 2. We'll loop out to the 3, and then loop back into the 7x. Your 2 came first, so you're going to write it first. The 3 came second, so you'll write it next as the power. Then you're going to set it equal to what came last, which in this case is 7x. So now you have a perfectly good equation, 2/3 equals 7x, that you can solve. Well, first off, 2 cubed, you put that in your calculator, 2 cubed is 2 times 2 times 2, which is just 8. So you just have 8 equals 7x. And then to solve for x, just divide by 7. And voila, x is equal to 8 over 7. And yes, you can enter 8 over 7 in the Hawks program. And if your fraction can reduce, please reduce it. Now, another example, similar to the last one. Once again, you got a log problem. Easy way to solve it is to loop it. The 9 came first, so you write it first. The 2 came second, so you write it second. And set that equal to everything that came last, which in this case is everything that is 2x minus 7. And there you go. All that's left for you to do from there is to just solve the equation. So 9 squared, go ahead and solve that. That should give you 81. And from this point, you just got to solve for x. Go ahead and add that 7 to both sides. And you'll get 88 equals 2x. And then divide the 2. And voila, you get that your answer is x equals 44. Done. Yeah, you guys probably remember covering this a lot in Algebra 2 last year. And now it's finally come back in college algebra. Now let's take it up a notch. These are some other loop examples, but they're a little bit more interesting. So let's try the loop method on this. So 125, loop to the 2/3, loop to the x. So the 125 came first, so I'm going to rewrite it first. And then all of 2/3 came second, so I'm going to write that second as the power. Some of you are looking at that already and you're going, ugh, yuck. And then, of course, the x came last, so you'll write that last. So yeah, x is equal to 125 over 2/3, but Hawk's program is not going to let you type that in. You're going to have to simplify it more. But remember from the bell ringer how I talked about how this is the power and this is the root? Maybe try rewriting it with that information. Let the 3 be your root. So in other words, you have the cube root of 125. And then your power is 2. So why don't you take all of that to the power of 2? And let's simplify from there. Well, cube root of 125, you plug that into your calculator, it turns out to be 5. And then you just have to do 5 squared. And 5 squared gives you your answer of 25. That just made me think of that SpongeBob meme. I don't know if any of you know about that SpongeBob meme, but we'll talk about it later. Moving on. Now, next example. This one looks a little weird because the log is in the power. Weird. Now, unfortunately, we can't do the loop method yet with this stuff. All I can do now is I can look at the 16. I wonder if I can rewrite 16 as a base of 4. Well, I know 16 is actually the same thing as 4 squared. Oh, look at that. You guys remember this from earlier this week. If my bases are the same, then my powers can be set equal. So in other words, I can take log base 3 of x, set that equal to 2. Ooh, look at that. Now I can do the loop method, where my 3 is here, loop to the 2, loop to the x. And sure enough, 3 came first, 2 came second, x came last. So there you go. 3 squared equals x, or 3 squared is 9. Done. Yeah, that one, if you didn't know about that, you probably would have just stared at that for a long time wondering, what, how? But now you know. Rewrite 16 as base 4 squared, and then use what you learned before. Piece of cake. Now moving on to some more examples. Sorry. Now these examples. Sometimes the Hawk's program will tell you just to figure out what this is equal to. And well, sometimes you might think you can plug it into your calculator, but you can't with this example, not yet. But what you can do instead is whenever they just give you log base 4 is 64, why don't you set it equal to x? Just go ahead and do that. Log base 4 64 equal to x. And then you can just use what you've done all along, the loop method. So in other words, 4 came first, x came second, and then 64 came last. And then from here, it's very similar to what you guys did earlier this week, where you can take the 64 and rewrite it as a base of 4. Or in other words, the 64, you can rewrite that as 4 cubed. And voila, if the bases are the same, then your exponents can be set equal. X equals 3. And you're done. Piece of cake. The second one, very similar. The Hawk's program will give you an example where they just say solve log of 1/6 base and then 36. And they won't have like equal to anything. So when that happens, just set it equal to x and then just do the loop method again. So take the 1/6, loop to the x, loop back, and go from there. So the 1/6 came first, the x came second, so 1/6 to the power of x equals 36. And now we just go and solve from here. Some of you may be freaking out, oh, that fraction, I don't like that fraction. Can I rewrite it so it's not a fraction? If you remember earlier this week, there is a way to take that 6 and rewrite it to the top. Or in other words, you can flip it to the top, but the thing is, you'll have to rewrite that as 6 to the power of -1, and then all to the power of x. And then the 36, you can probably guess we're going to have to rewrite that as 6 squared to try and get our bases the same. Moving on from there, you'll have to multiply the -1 and the x, so that just gives you -1x or -x. So x and -6 equals 6 squared, and voila, your bases are the same, so you can take your powers and set them equal. So -x equals 2. Then just divide that negative sign or that -1, and you get x equals -2. Done. Make sure you got all the notes on that one. That one's going to be a little tricky. And yeah, you're definitely going to come across the example. You might not remember how to do it, so you'll come back to this example and follow the guidelines. And with that said, those 2 examples are good. Let's move on to some other examples. If you have your calculator with you, I want to point out these 2 buttons here, the log function and the ln function. Now, some of you are probably thinking, Miss Shulin, if log was in our calculator, why didn't you just teach us to use our calculator? Well, here's the thing. This particular log only works if you have a base of 10. All the other examples we've had have not had a base of 10. Look at all those examples. Do you see a single base 10? No. For some reason, the calculator will only give you the log of base 10. And for this natural log that I'm going to talk about later, it's the same thing as log that has a base e for that exponential function I showed you a couple days ago. That one's a little weird, and I'll explain that more in detail at a later time. But all you need to know right now that in your calculator, this particular log button is log base 10, and this ln button is a special type of log that has a base of e. That's all you need to know right now. On the next slide, I just talked about the exact same thing I mentioned. Log base 10 is the log in the calculator. And log base e is a special type of log called ln. Or in other words, it's the natural log. If for some reason they didn't put NL for natural log, they decided to flip-flop them and put LN for natural log. It is very, very confusing. But just so you know, the ln that you see is natural log. And just in case, if you ever see any of these problems where it doesn't give you the base, you can assume that's base 10, and then this natural log is log e, and then you can just type any of these types into your calculator. Like if you type the first one in, you'll get 4, you type this one in, you'll get this, you type this one in, you get that. Easy points on the homework. As long as you know, okay, that's the type of logs I can plug in the calculator. Any other log that doesn't have a base 10 or a base e, you got to do the loop. Just had to point that out. Okay, so now I need to talk more about the natural log, or ln. Now, the natural log, as you know, we talked about how it's the same thing as log base e. It turns out that natural log and the e have a very special relationship where if they're ever next to each other, like directly next to each other, they cancel out. And then all you'll have left is that power of x. So then x is equal to 23.5. It's weird, right? But if you recognize that, it makes solving really easy. Like in this example, look at the e, look at the natural log. They're right next to each other. And if they're right next to each other, you can cancel them out. And all you'll have left is that little x in parentheses. So set that equal to 23.5, and you're done. Easy peasy. Now look at the examples on the right. This time, the natural log and the e, they're not directly next to each other. There's a root in the way. However, remember, you can do power on top, root on bottom. Sorry. Power on top, root on bottom. So the e can be rewritten as e to the power of 5 over 8, where 5 was the power, 8 was the root. And then all of that being multiplied by the natural log. And now look what you've done. Natural log and the e are now officially next to each other. So cancel them out, and all you have left is that power of 5/8. And 5/8 will be the answer that you type into your calculator. The second one, very similar. You can't really eliminate these two because of that root in the middle. But I can rewrite the e as power over root. Or in other words, power of 2 on top, root of 4 on bottom, and the natural log on the side. Voila, they're now next to each other, so you can cancel them out. And all you're left with is 2/4 as your answer. But you'll need to reduce that down to 1/2 as your final answer. If you do not reduce your fractions, the Hawks program will count it wrong. So be wary of that. All right. Seems easy enough. Now, there's another type example I need to cover with you real quick, and you are going to need your calculator with you if you have it on you. Now, these type of examples are a little tricky. Now, remember how I talked about the natural log is the same thing as the regular log with base e? Well, it turns out we can make this problem a bit easier to solve if we replace this natural log with log base e. And then everything else, the 5x plus 2 and the 4, stays as it is. The reason why I'd want to change this natural log to log base e is so that I can do the loop method, where the e comes first, the 4 comes second, and the 5x plus 2 comes last. Let's go ahead and do that over here. E comes first, 4 comes second as the power, and then you'll have to do 5x plus 2 last. And now all that's left for you to do is to solve for the x. First, we'll subtract the 2. Well, you can't really subtract 2 from e to the 4, so you'll just have to do that. E4 minus 2 equals 5x, and then divide the 5. So then you'll have e to the 4th minus 2 all over 5 equals x. Now, the Hawks program will not let you put this in as your final answer. You actually have to plug that into your calculator. So, give me a second. I need to rewrite this as e to the 4th all minus 2 all divided by 5 equals x. Now, I recommend you do the top part first, and make sure in your calculator to put this 4 in parentheses. So, I'm going to do that over here. I'm going to do e to the 4th minus 2 first. So let's do that. In the calculator, e to the 4th, put the 4 in parentheses, and then minus 2. So then on top, I'm going to get approximately 52.5981. And once you have that number, then divide it by 5. Whatever you do, do not plug that entire thing in the calculator all at once. So then your final answer will be approximately 10.5196, approximately. I'm pretty sure the Hawks program will have you round to 2 decimal places. I'm just putting extra just in case. Like again, do the top first. And once you have the top, then divide by 5. Let's try another example like that, just so you get the hang of it. So here you have natural log of 2x plus 6 equals 5. But I'm going to go ahead and take that natural log. I'm going to replace it with log base e. And then 2x plus 6 equals 5. And then, now that I've done that, I can now do the loop method. E is here, 5 is second, 2x plus 6 is last. So now, let's just write that out. E first, 5 came second, and then the 2x plus 6 came last. Then let's go ahead and solve from there. I'll go ahead and subtract 6 to both sides. So that's e to the 5th minus 6, all equals 2x. And then divide by 2 to both sides. And then I'm just going to put that over here, make some space. I'm going to put that over here, e to the 5th minus 6 all over 2 equals x. Now, like before, I'm going to do the top first. And please put that 5 in parentheses when you solve. So let's go ahead and do that over here. So on top, I'm going to do e to the 5th in parentheses and then minus 6. And that's going to give me 142.4131 approximately. And then once you have that number, then divide by 2. And that will give you your final answer for x, which is going to be approximately 71.2066 approximately. I'm pretty sure they'll have you round to 2 or 3 decimal places. I'm just rounding this much just in case. All right, that's probably going to be the hardest one in the book. Now, last example, I have to cover it because this has been a tricky problem because of one reason. And that reason is that students do not read the instructions. So let's go ahead and read the instructions. Write the following equation as an exponential equation. Do not simplify your answer. Now let me explain. So let's say you get an equation that looks like this. Well, first off, most people would try the loop method. But here's the thing, the log is on the wrong side. We're used to log being on the left. Well, never fear, you can flip-flop these so that you have log base little c of big V equals 2x. It is very crucial that you keep the c little and the b big, the v big. So now that you flip-flop those two, let's do the loop method. Here, here, and here. So the c came first, the 2x came second, and the v came last. Now, a lot of students will get to this point and say, oh, Shulin, that looks very, very weird. I don't know if I did this right. I don't know what to do. What is up with this problem? But now, look at the instructions. Write the following equation as an exponential equation. You don't have to solve, you just have to write the equation as an exponential equation, which you have already done. And it also says here, do not simplify your answer. So in other words, once you get here, you're done. That's all you had to do. That's all the instructions asked you to do. It just wanted to make sure you knew how to do the loop method. Now, I know some of you will probably attempt this problem and wonder what the heck is going on, then you're probably going to ask for my help and say, Miss Shulin, I don't know how to do this problem. And I'm going to point to the instructions, and you're going to be like, oh. Hopefully, this does not happen to you. I hope it does not happen. But I will say that if it does happen, you have been warned. And with that said, the video is now complete. You may now start on your online homework. You all have a wonderful day.